I have some interest in that. If you'd like to find out more.
What's your
Things like you will study in P29. Electromagnetic waves.
So it sounds fun.
I don't know what we've learned since the last.
Okay, let's get started. So we know about Fourier series. Sometimes it's also called Fourier expansion. And it says that if you have a periodic function f of t, then it can be expanded in terms of the sum of periodic function e to the j n omega naught t. Okay, n goes from minus infinity to infinity. Okay, you can see that this is periodic, and this is also periodic. Okay, and if these two conditions are satisfied, then this expansion is true. And then examples of a periodic function I can draw for you. F of t might look something like this. Say, let's draw the period first. The period is t. Minus t, 0, t, 2t, 3t. So if I were to draw a periodic function, it might look something like this. Okay, so this is a periodic function. Any arbitrary periodic functions can be expanded in terms of a Fourier series. This repeats itself. Okay, that is what Fourier said. And how do you find the coefficient f sub n? F sub n is given by 1 over t e to the minus j n. It can be n omega naught t f n of t, and you integrate this over one period. Okay? And that's how you find all the Fourier coefficients. This is also known as the Fourier coefficient. Okay? So if I give you a periodic function, the rest is just hard work. Did I miss something? F sub n, right? Sure. N.
No, the
dt. Very good, dt. Okay? So if you're asked to do this work, the rest is just hard work. If I give you f of t, f of t, find f sub n, it's just hard work. Okay? You can do this hard work many, many ways. One is to use your knowledge on calculus to do the integration in closed form as much as possible. Another way is to write a computer program to do the integration numerically, but we will not talk about that. We talk mainly on how to do this integration in closed form. Okay, there will be lots of algebra. And so you need to only know a few fundamental integration rules in this course in order to do those integration well. First, you have to learn how to integrate a function such as this one. Okay? That we know how to do, right? Then you get e to the j alpha t divided by j alpha 0 to t. And then you get e to the j alpha t minus 1 over j alpha. Okay, there's one rule that you have to learn repeatedly in this course. Okay. Another rule that you need to learn is this one. How do you integrate e to the j alpha t times t dt? How would you integrate something like that? What is that? Unit substitution? No, there's another rule of integration that you learn in high school. Integration by parts, very good. You do this integration by parts, and first you integrate this term first. Okay, if you integrate that term first, you get e to the j alpha t over j alpha 0 to t minus the integration result of this one, j alpha, and what do you substitute in here? The derivative of this, right, with respect to t. And then you just get 1 dt. So if you have to integrate the function, it will be j alpha t minus 1 over j alpha for the first term. And then the second term, you just do it over again, is 1 over j alpha. Okay? The integration of this one, which is e to the j alpha t minus 1 over j alpha. Okay? So I think those are the two main things that you need to learn how to integrate. The rest is just hard work and care, making sure that you don't make errors when you do all those complicated integration. Okay, how many of you do not know how to do integration by parts? Okay, let's see how we can do that, okay? So if you have a product of two functions, you know that this, using the chain rule, is equal to that. Okay, that follows by chain rule. And then if I integrate this equation, say dt to t, say something like that, p prime or something. Okay, if I want to integrate that, then the integration of the left-hand side is what? It's a closed form solution, right? It's a closed form solution. It goes from, say, if I go from 0 to t, the left-hand side would just be 0 to t prime. Okay, that is what the left-hand side is. And then if I integrate the first term, okay, u dv dt, dt 0 to t prime. That's what I get for the first term. And then I get the u dt, v dt 0 to t prime. Okay? So what it allows you to do is that you can write an integration of something in this form if you notice that one of the two terms is an exact derivative. This is a derivative of something else. Okay? So you can always write 0 to t u dv dt dt is equal to uv 0 to t prime minus du dt v dt 0 to t prime. Okay? I was essentially using this formula over here. Okay, I know how to integrate this in closed form. I think of this as dv dt of some sort. Okay? I think of this as u of some sort. Okay? When I apply this rule, I can figure out what v is. What kind of v would give me that? I just integrate this one to get v. That's essentially what I have for the first term over here. And then I actually have to have t, actually. I have to put t here. I actually have to put t here. Okay, so I actually have to put a t there. So I have to figure out what v is and then put the u. My u is t. My dv dt is e to the j alpha t. Okay? And then the first term I have to substitute is to put in my u, which is t, and then my v, which I figure out to be v is equal to e to the j alpha t over j alpha. And I substitute in there, I get this first term over. Okay, then the second term, I figure out what my v is. My v is already this, okay, which is this one over here. And then the u dt, my u is just my t. Okay, the u dt is just 1, so I get the second term over here. Okay, and that's how you do integration by parts. Okay? So the rest is just hard work. Now let's do an example. Say f of t f of t is the magnitude of sine of t. Magnitude. So this converts a sinusoidal function into something that is always positive. So this is a periodic function for sure. Okay, where is this value that it goes to 0 again? T equals to pi, 2 pi, 3 pi. So this is a function with period of pi. Okay, it goes on and on. So we can find the coefficient f sub n to be 1 over t, 0 to t dt, sine of t e to the minus j n omega naught t. And then my t is pi. My omega naught should be what over here? What should I use for omega naught for the period of this one? 2 pi over t, right? 2 pi over t, but t is pi itself, so this is 2. Omega naught equal to 2. Okay? Then let's substitute in and do integration. If I do it carefully, without making any mistakes, and it's difficult to integrate sine and exponential functions, right? So what do I do to the sine? Convert it into an exponential form. Okay, so the sine can be written as e to the jt minus e to the minus jt divided by what? 2j. Okay? And then you multiply by e to the minus j. Omega naught is 2, so you can put a 2 here if you want, and then do a dt. And now you can integrate term by term after you have combined them. Yes?
Why is it the magnitude of sine of t and f of t, but then when you solve it for the coefficients,
What is that again?
you don't have it as the magnitude in the formula for f of n?
Oh yeah, I should put the magnitude here because I'm integrating from 0 to t is positive anyhow. Okay, it's positive, always positive. I can put the magnitude sign or not. It doesn't matter because I'm integrating over this range. Okay, if I don't put the magnitude sign, then I'm comfortable with applying the Euler's identity, the trigonometric identity for sine. Since there's actually no magnitude needed there. So I can substitute this with that. Okay, you can put a magnitude there with the understanding that in this range, this is always a positive number, magnitude doesn't matter. So I can use this Euler's identity in there anyhow. Okay? So, and I can do that term by term. That's a good question because some of you may not understand why. So I can actually multiply things up. There's a 2 dt here. F sub n is equal to 1 over t 0 to pi dt. I can put a 2j outside. And then I can combine terms. E to the minus j n to t minus 1 is my first term. And then minus e to the minus j n to t plus 1. Okay, I integrate term by term now, and I know how to do that. So it's t times 2j. The first term will give me e to the minus j. There's a t here, sorry. There's a t here. There's a t here. And better write this as n2 minus 1t. n2 plus 1t. Okay? So if I integrate the first term, then I get j n to minus 1 t over minus j 2n minus 1, okay, minus e to the minus j 2n plus 1 t divided by 2n plus 1. And then I have to evaluate this at the two endpoints. 0 to t, t is actually equal to pi here. Okay, this is pi. T is equal to pi. And then I have to evaluate the two endpoints. And there should be a j here. Okay, there should be a minus j there. And then if I evaluated the first one, and I must well take this minus j on the outside, okay, and then I evaluate this at the top point, I get e to the minus j 2n minus 1 pi minus 0, give me 1 over 2n minus 1 for the first term, and then the second term is e to the minus j 2n plus 1 pi minus 1 over 2n plus 1. Okay, the rest is just algebra. And what is 2n minus 1 pi? E to the j of 2n minus 1 pi. 2n minus 1, is that always an even number or an odd number? 2n minus 1. Is this an even or an odd number always? It's always odd. Okay? If this number is always odd, e to the minus j times an odd number times pi is always equal to e to the j is always an odd number. It's always negative 1, right? Negative 1, if you go around in a circle, you go 1 pi, 3 pi, 7 pi, right? Odd number, 1, 3, 5, 7, and so on. You always end up with this point, always negative 1, right? So that always gives you negative 1. And then the second one, 2n plus 1 is always an odd number. It always also gives you negative 1. So the next line should be, this combines with that gives you 1. T is actually equal to pi. Okay, so I can put pi over here. T is always equal to pi. And then if I do everything correctly, it's minus 1 over 2n minus 1 for the first term, minus 1 over 2n plus 1 for the second term. Okay, so it's actually minus 2 over 2 pi, so it's 1 over pi. Okay, 1 over 2n minus 1 minus 1 over 2n plus 1. You can simplify it by bringing them under the common denominator. Okay, we bring them under the common denominator with minus 1 over pi, 2n squared plus 1 b squared, right? A squared minus b squared. So it should be 2n squared minus 1 and then 2n plus 1 minus 2n plus 1 over here. Okay, bring them under the common denominator, you get this minus 1 over pi to be, this cancels with that, you get 2 over 2n squared minus 1. Okay, so this is your f of n. And in my note, I have the answer to be 2 over pi is 1 minus 4n squared. Bingo, I got it correct. Okay, so bingo, I got it correct. So that is f of n. Okay, does anybody have any question on the algebra? It's all algebra and hard work. If you are very good at that, there are many 100%ers in this course. I'm sure that you can get them down packed and correct all the time. Okay, since you score 100% in your last test. So go through this algebra. Yes?
I keep getting lost between the capital T's and the little t's. Is there a significance
or capital T is a period. It's usually used to denote the period. T, this is the variable, the time variable in time. So T, little t is always changing. It's something that has not a fixed value. Capital T is something that is fixed in value. It represents the period. And in this picture, you can see that the period is pi. So capital T is the same as pi. Okay, as I denote here, as I have denoted here. Okay, little t is a variable. It will be a variable of integration. So if you do that correctly, then you get this thing. But you just have to remember two integration rules. Integration of an exponential and integration of an exponential multiplied by t. If you know how to do that two integration, you're set for this course. And then this course also asks you for the compact form. You can rederive the compact form, but that probably is too difficult. Okay? You probably say, remember that compact form is something of this form. Cn, n equals to 1 to infinity cosine of n omega naught t plus theta. Okay, that is a compact form. And then you just have to remember that C naught or Cn is 2 Fn. That has been derived before. So C0 C0 should be equal to Fn over 2, F0 over 2. Okay, I think this is correct. Let me see, that's not correct. This should be C0, is always put as C0 over 2 in the textbook. So let me put C0 over 2. I think the textbook always uses this notation. Okay, C0 over 2, that's what the textbook uses. Okay, that's the DC term. The DC term is always equal to F0. Okay? So if you do that, then this formula agrees with this formula. This formula agrees with that formula. And C0 over 2 is always equal to that. Okay? And this is always F0 in the exponential form. Okay? And then in order to get this into the compact form, you identify what F0 is. F0 is equal to 2 over pi. Okay, F0 is equal to 2 over pi from this answer over here, set n is equal to 0. So C0 over 2 is just F0 is 2 over pi. Plus n is equal to 1 to infinity. Cn is equal to 2Fn. So you put a 2 there, and then your Fn is this one over here. What is that? Did I get it correct? C0 over 2 is F0. Fn is equal to that is F0 is 2 over pi from here. Okay? But the first DC term is always written in this way in the textbook, which is the same as F0, the DC term, the static term. The static term is 2 over pi, so I put the 2 over pi there. Okay? And then I have to take the magnitude of f sub n, which is the same as 2 times the magnitude of this, which is 4n squared minus 1. Okay, cosine of n omega naught t. Omega naught in this problem, where did I work out omega naught? Omega naught is 2. Okay, you can put omega naught equals 2 here. And then what is the phase of this number? The phase of this number is the phase that you're going to put here. This number is always positive or negative. If you look at this number, n is always running from 1 to infinity. So this number, which is f sub n, is it always positive or negative? Yes? N is always greater than 1, right? So this number is always negative. So if you work and rewrite it in the form that is always positive, then the phase has to go in here. So you put a pi there. This is a compact form that the book asks for. Okay? Are there any questions regarding on how to convert an exponential form into a compact form? Somehow the book likes compact form. I always ask you to do that. Yes?
Can you repeat how you got the phase angle at the very end?
On the phase angle, okay, theta is the phase of f sub n. Okay, and that we have worked out before. And if you don't remember, you can go and look at the textbook or look at the lecture notes. Theta is going to be that. F sub n is given by this number over here. Okay, this number is always a negative number because 4n squared is always larger than 1. N is running from 1 to infinity. So f sub n can also be written as a positive number, pi 4n squared minus 1 e to the j pi, where this is always a negative number, and hence if I think of this as e to the j theta, theta is pi. I put this pi in there, I get this number over here. Okay. Are there any questions regarding how we get that? Yes, Tom?
May I ask, how did you know what f0 was, or how did you figure that out?
F sub 0, because I have this general formula for f sub n. F sub n is given by this general formula, which is derived using this formula.
Right.
Okay, I worked through algebra, and miraculously I did not make any mistakes, and I end up with that thing.
Okay.
Okay.
So wouldn't it be the whole thing then? Why is it just 2 over pi?
Then I set n to 0. F sub 0 is, when n is equal to 0 in this expression, then the 4n squared goes away, it gives 2 over pi. Okay, so F sub 0 is 2 over pi. Okay?
Thanks.
And there's a pi missing here, missing this pi. So I should put this pi back there. Okay, so you can simplify if you want to, you get some other things. So the rest is just algebra. You will have to do lots and lots of algebra in this course. And there's another property that if f sub t give rise to Fourier coefficient that are f sub n, okay, f sub t minus t naught, a function delayed by t naught, give rise to Fourier coefficient that are given by j n omega naught t naught, okay? This is a rule, and we can prove this rule very easily because we know that f sub t is equal to f sub n e to the j n omega naught t. N goes from minus infinity to infinity. So by direct substitution, f of t minus t naught must be the same as this thing. And then just replace t with t minus t naught. Okay, this must be true. And then I rewrite the right hand side e to the minus j n omega naught t. I use the product rule for exponentials and write this as two terms. Okay? And then this is my new coefficient, my new Fourier coefficient f n prime. Okay? So I see that my new Fourier coefficient is just equal to that, which is exactly the same as that. Okay? Everybody get that? No problem, right? No problem, no problem. Okay? So, example 6.7. Find the Fourier series expansion of this function. Okay. Find the Fourier series expansion of this function. And again, if you look at this function, it will look something like this. So what is this value that it goes to 0 over here? Pi over 2. This value that repeats itself is again pi. 2 pi. And then this goes to minus pi over 2. Okay? So the trick here is to find a clever way to do the integration. What is that?
Can't you just integrate from 0 to 3 pi multiplied by 2?
You can integrate from 0 to pi over 2.
So multiplied by 2.
Not necessarily.
Have the answer shifted by t hat.
You can also do that. If you're clever, you can use the time shifting property and find the Fourier coefficient that way. Okay, or you can, you can do that too. You can use the one that you have found for sine and then add a phase shift to that, and that gives you the Fourier coefficient for this
Didn't know
series.
the sign.
I erased it.
No, I mean, if we didn't know it, let's say if it was like.
Okay, then you have to start from first principle.
Yeah.
Okay?
Or you can memorize it.
If you don't memorize the one for the sine, when you start from
Sure,
first
memorize
principle,
every possible
So-
function there.
that we call the coefficient g sub n is given by this. E to the minus j n omega naught t dt. And in principle, I have to integrate this over one period. Okay, it doesn't matter whether I integrate from here to here. I can also integrate from here to here. Okay, there's still integration over one period, right? Because this is a periodic function. So this part of the function as well as this part is the same as this part of the function over here. Okay, so I may as well integrate from minus pi over 2 to pi over 2. Okay, it's the same. You can convince yourself that this is the same. Integrating from here to there gives you a lot of agony because you have to worry about the sign change, the magnitude change. But if I integrate from here to here, I'm actually integrating the same thing. And the cosine doesn't change sign. And I can now replace this with no magnitude sign. Then I can use the Euler's identity for my cosine. And go to the next step.
Why couldn't you just integrate over the half of the equation multiplied by 2? Wouldn't it be the same thing?
Not the same because the phase is not symmetric. Okay, so what happens is that Georgie suggested that I integrate from here to here and multiply by 2, but this thing is not periodic over there. So it doesn't replicate itself, and if you do that way, you do it that way, you find that the answer is wrong. Okay, but if you do it this way, this part, the phase of this function over this part is exactly the same as the phase of that function over this part. Okay? But the phase of this function over this part is not the same as the phase of the phase function over this part. So I cannot just integrate from here and multiply by 2, because this integration is actually slightly different from this integration because of this phase function. Okay? However, this phase function replicates itself over here because it's also a periodic function. So I can integrate from here to here. So when you want to do a shortcut, make sure that this phase function is also replicated over the place where you want to take shortcut. Okay? So if you do that, then everything is just straightforward algebra. You expand the cosine in terms of exponential form, collect terms, do the integration correctly, then you should get the correct answer. Okay? So if I give you the fact, example 6.8, okay, if I give you the fact that you already know how to find the Fourier series expansion of this function, okay, you know how to find it, and we found it successfully. We found it to be this one, 1 minus 4n squared e to the j 2nt. Okay? Then you're asked to find the Fourier series expansion of a new function which is given by sine of t over 2, magnitude squared. Okay, yes?
Should that one have added to?
No, this is not the compact form. This is the exponential form. Exponential form has a DC term embedded in this sum. When you have n is equal to 0, it picks up the DC term. Okay, when n is equal to 0, the static term is there. So in the exponential form, there's no extraneous C0 over 2, A0 over 2, not that kind of thing. I like the exponential form the best because it's clean. You only have, there's one thing to remember. The compact form, you have to figure out what the DC term and what it should be and that kind of thing. Okay, just remember the exponential form. Okay? Exponential form is, I erased it somewhere. So how do I find the Fourier series expansion of the second function? The first function we found to be pi periodic. F of t was something like this. Pi, 2 pi, 3 pi, and so on. Okay? What is the period of the second function? Yes? How big must t be before it reaches, the argument reaches the value of pi? T must be 2 pi, right? So is the period larger or smaller? Twice as large, right?